what your lecturer is saying, you're doing a good job. Because math turns out to be pretty hard, and it's pretty time and energy consuming. And usually after you saw somebody's lecture, you go back, you write list of questions you have, and it's very stupid because the lecturer already sends it. You're just gonna go and ask him again, and you would read his or her notes again, twice or 3 times, but instead you're gonna understand that. Or it would be half a month, and you learn some other topic, and it just strikes you that you actually now understand the second topic too, because you had at least some base. So I mean, what we are trying to do here is trying to teach you cool math and give you some background. Because today, if you didn't notice, you actually understood what cardinality is. You understood that natural numbers are countable and real numbers are not countable. And we couldn't just teach you textbook and set theory, but we think that's not very fun, So we just cover basic facts in very cool topics that are actually pretty advanced. And if you don't understand the advanced topic, at least you got the basics, and now you have some background. So yeah. Okay, so remember how our infinite games goes. We have 2 players, and we have axiom of determinacy, which tells us there is only strategy for one of the players. So let's just make up a game that would lead us to a conclusion that all sets of Lebesgue measurable. Why not, right? Because now we have this powerful fact that each game is determined already. Okay, so imagine that we have this is year 1. You're gonna see it in your nightmares. Okay, and there is some given set on this interval. And you have 2 players, player 1 and player 2. And you also is given some number b. It's already given to you before you start the game. So basically, the aim of the first player is to show that the measure of the set is at least b. And the second player is trying to show it's not actually true, that the first player is lying to you. The way they do it is the following. So, let me just wait. Also, you might have points of a given set. So the way they do it is the set is, the whole interval is divided into 2 halves. And basically, the first person comes up with Q1 and Q2. And the thing is that Q1 plus Q2 is strictly less than D. What are those Q1 and Q2? It would be the measures of the set on this side, Q1, and the measures of the set on this side, Q2. So basically, if the first player would be able to show that the measure here is less than Q1, and the measure here is less than Q2, or less than equal to Q2, then the sum of it is less than B. That means the whole set's measure is less than B. Oh, I told you. Okay, so he's trying to show that the measure is less than B. Okay, yeah. Okay, so basically, that's what he's trying to do. And second player is no, you're wrong. The way second player can do that is second player gets to choose one of the halves of the intervals. Either this or this. That she's gonna check. And okay. So basically, the first player has just one small thing. So imagine that that you have a set that just totally covers one of the halves. in this case, the first player is able to say, I don't want to prove anything about this set. Like, that's not fair. You just have to play on this interval only. Okay? And so second player just has to choose this interval. Because first player didn't guarantee anything about this half of the interval, right? Because the measure of this interval was just full. So it was kinda unfair to the first player. You'll see why. Okay. So the game goes like further and further. You divide this interval into halves. And now you have new Q1 and Q2. Okay, let's call them like this. And you have to show that Q1 plus Q21 are less than Q1. And first player assigns those values, like he chooses those values for the measures for this set. And the second player can just choose what interval she wants to check. Like say she wants to check this interval. Then you divide it again into 2 halves, and you do Q1, 2, Q2, 2, and then she checks again another interval. And the game just like goes like infinitely long, right? But if you divide interval infinitely long in halves, you'll reach a point after like infinite amount of moves. So the game would be as following. If the point that they reach at the end of a game is in the set E, that you needed to prove that its measure was less than B, then basically the second player wins. It's into E, then second player wins. If it's not into E, then the first player wins. Okay, how is this at all like connected to our Lebesgue measures and blah blah blah? Basically, because if you would be able to give boundaries to sets, that would help you show that it's measurable, and you'll see at the end how it works if we'll get to the second part of the proof. It probably will not be today. Okay, so what is interesting here? We forgot about axiom of determinacy. We'll apply this magic axiom of determinacy to here. Well, one of the players suddenly has a winning strategy. Great. So what happens is that if a first player has for example, the winning strategy, that means that at the end, this point would not be in the first in the given set. And what it means for us is that measure of A is strictly less than B. So basically, if the first player has a winning strategy, the measure of the set E is less than B. Right? Okay, great. So the way we're gonna prove it is the following. Okay, so let's just see that you always would have a specific set of intervals, let's call them G, and those intervals are the intervals that first person denied to guarantee. And basically, if you take all possible games and all the intervals G that the first person denied to guarantee, all other points actually would not be points on the set E. They would be out of the set E, right? Because like, if in some game, like, there was like a point in the game, like that was not lined in the set G, then the first player loses because they reached the point that they should not reach. Otherwise, the second player wins. That means, but we know that the first person wins. That means that like all those points would be in the intervals G, but the first person denied to prove that they have some values. Okay. Yeah.
Excuse me. Just to clarify, what's the relationship between V and E?
V and E. Okay. So E is a set.
Yeah.
Set of points that we had, right? And V is a given number that was just given to us at the beginning of the game. And basically, we are trying to prove that the measure of E is less than V if the first person has only strategy. So basically, if they play, and the first person is always able to reach a point that is not in the set E, then it means that what he claimed actually was always right. The sum of the stuff would actually sum up and be less than V. Okay? So, I mean, that makes sense, right? Like, imagine they have some source V, and you're trying to prove, okay, imagine you have, okay, that would be a weird example. Imagine you have like a bunch of flowers, and measure is when you are able to cover the whole interval with flowers. And if the measure of the set is less than like this amount of flowers, then that means the first person was able to win. That means he was able to always assign some specific amount of flowers on each of his steps, and they always cover the intervals. So, like, in any way, whatever interval second player would choose, the first player would always be able to cover them with flowers. At some point, they would just reach a point, and it would not be a point in E, so it would not be needed to cover it in flowers, and it means that the first person actually was able to cover everything in flowers. Was it a good example? I mean, okay, it gives you an intuitive sense of what's happening. So yeah, basically now we do a bit of analysis here. Okay, so we see that the sum of this measures of intervals G is just those intervals that we do not guarantee have like we do not guarantee to prove values for, is less than V3. Then, because in Lebesgue measure, we have to put everything in open intervals. I'm sorry, how about it? So we have those closed intervals, and in Lebesgue measure, we want to put everything in open intervals, right? We're just gonna put an open interval on each of those intervals of G, okay? Okay, like we just put intervals, open intervals around those. Okay, good. So that means that the measure of those open intervals would not be equal to measure of G because they're just a bit bigger, right? It would be some measure of G plus some little epsilon, just like a bit of extra stuff, right? Okay? Okay. And we do this for every interval here. The thing is that we are controlling this epsilon. We are controlling how close those open intervals would be to the initial intervals. It means we're able to do this epsilon very small, like just like very small. Like if you have this interval G, you'll be able to like move those open brackets as close as you wish, making the difference between the measure of entire open stuff and measure of G just very small. Okay? And we just can do this for every interval that the first person did not claim any value. And then we just sum up all of those, right? We just sum up all of those intervals. We get their sum plus sum of some epsilons, right? And we know that their sum is strictly less than b. That means that their sum is sum a equals to v. Like, right, their sum plus a equals to v. Okay, so we always would be able to make some of those little epsilons less than a. Okay? What it tells you is that we were just able to cover all of the intervals with open intervals, and that they are still not bigger than b, and this stuff is equals to measure of our set E. Right? So that's how we define Lebesgue measure. Lebesgue measure is just sum of measures of open intervals. We put in open intervals around them, yes, with it. And this measure is still less than b. So we did a claim. We actually proved that this measure is less than b using the assumption that the first player won. Right? Okay. Is that intuitively understandable? Do you need to repeat any part of that proof? Kind of proof. That's not a very active proof. Okay, I see some.
A little bit.
Okay, which part was not understandable?
The epsilon and the plus a part, like nearly the end.
Okay, that's actually a very good sign, because I was like saying that you didn't study before. Okay, so let me just give you maybe like a physical example. So imagine that you have those like intervals, and you know for sure, like say it's 2, that's 1, their sum is less than 5, and 5 is your v. Okay? And this is the sum of your interval j. Okay? Okay, so you know there is plus 2 that you can add to see that make it 5, right? I mean, I'm not here to like teach you like first grade stuff, and you know. Okay, so we would be able to choose very close open intervals so that this stuff here, like a very additional stuff, would be say like 1/2 and 1/2, and their sum is just 1, right? So like we just add a bit to those intervals, and what we add is just 1. So we add plus 1 here, and it's still 4, and 4 is less than 5. It's because we are able to control how much do we add. Okay? Say for example, we have like this 2 and 2, right? So their sum is 4. We have that the value v is 5. Okay, let's do this. Let's do like a very, imagine we have n intervals, like first interval, second interval, third interval, and you know that their sum is 4. Okay? And so basically, you know that your value v is 5. So there is distance 1 in between those two numbers. It means you can add open brackets to those intervals so that what you add doesn't go more than 1. So just how about we do open brackets that would be bigger than the interval by 1 divided by n. 1 divided by n. We sum up all stuff that we added, it's just 1. So we added plus 1, and now it's just equals to 5, but like, it's still less, okay, let's say we did n plus 1. Right, so then we add them, and you have n divided by n plus 1, stuff that we added, 4 plus n divided by n plus 1 is still less than 5. Great! We were able to put open brackets on closed intervals and still not go more than v. Okay, and open intervals is what we need for the Lebesgue measure. So if we have open intervals, we have measure of e, and it's still less than v. So that was our claim, we proved it. Good. I'm not gonna prove you today why if the second player has a real strategy, that would mean that the measure E is actually more or equal to V. I mean, yeah, if that wins at this, if he wins at this, right? Because those things are opposite to each other, and those things are opposite to each other, okay? Okay, but in a bit, to give you like a big picture of what is happening here, it would be this. You have different kinds of games. So imagine a game 1, and in this game, the V was like 1,000. And imagine that the first player won. Yay! That means that V, 1,000, is actually bigger than measure of E. Imagine the second game. V equals to 999. The first player won. It means that 999 is bigger than measure of E. Right? And imagine like a different, like opposite side of it. Like imagine some other game, and V was 0. Oh, that is too bad for the first player. So let's assume that the second player won. That means that the measure, wait, what am I doing here? Yeah, that means that the measure of E was bigger or less or equal to 0. Imagine a case when V was 1, still a bit too small, you know. The second player won. Measure of E bigger or equal to 1. Does anybody see a kind of nicely plotted picture coming in here, you know, like from both sides? At one point, there would be some V for which they just meet. Because our V doesn't have to be natural numbers. Our V can be like 999 point blah 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 blah. Right? It can be any number. So here our measures would just suddenly come together, and at this particular point we'll claim that this particular V, when this comes together, is our Lebesgue measure of the set E. Ta-da! We just showed that there is actually a measure for the set E. Isn't that cool? Okay, does it like? Do you understand this picture? Like how you just like how for some big V's that are too big, they are bigger than the measure of E. But then you make them smaller, and at some point there will just be a measure of E. And the same here, like they are just too small for measure of E, but at some point they'll be perfectly the measure of E. So there exists a measure of E. That means because of axiom of determinacy, all sets like measuring stuff, if you have a measure for a set, that's so great. You can do so much things with those measures, right? And so this thing gives you a very powerful condition. So yeah, that was the beauty of how you can play games and prove cool facts in maths. Thank you so much for coming to this lecture. I hope it was mind-blowing.